Hi everyone, so welcome to this meetup. So today we are pleased to have not one but two speakers. So we have Duhyeong Kim, who is a research scientist at Intel Labs, and we also have Gabrielle Micheli, who is a postdoc researcher at UCSD. And today, so they'll talk about amortized bootstrapping for FHEW. So thank you.
Okay,
I think Duhyeong, you're starting, yeah.
Okay, let me start with sharing my screen first. Okay, can you see my screen?
Yes, all good.
Okay, great. So thank you for joining the talk, and also we really thanks to FHE.org organizers for providing a very great opportunity to introduce our work to the community. Today we'll talk about our recent work on the amortized field bootstrapping, which is one of the mainstream of the state-of-the-art FHE schemes. So as Mark mentioned, the talk will be presented by myself and my co-author, Gabrielle Micheli from UCSD. I'll take the first half explaining the high-level overview of our work, and then I'll back and touch to Gabrielle. Okay, so basically there exists two different types of FHE schemes. One is bitwise FHE, which encrypts each bit of the message separately in each ciphertext, where FHEW and TFHE, these schemes are typical ones. The other branch is wordwise FHE, which encrypts the whole message, even multiple messages in a single ciphertext. And BGB, BFV, or CKKS schemes are in this type of the schemes. So those types have very pros and cons. So in terms of latency, actually the bitwise FHE schemes shows much faster performance compared to the wordwise FHE, because the bitwise FHE, it starts with less than a second, and then it was improved like less than 0.1 seconds, like that. So it takes only a fraction of seconds, but in wordwise FHE, it takes at least several minutes, and it can be more than that. But in terms of the amortized running time, the latency per each bit of message, then the situation is reversed. So in this case, the amortized running time for this FHEW and TFHE is just as same as the latency. But in BGB and BFV or CKKS, because it has very large message space, the amortized time goes down. It gets smaller than the amortized time of the FHEW and TFHE schemes. So in this perspective, our work focus on the amortized cost of bitwise FHE bootstrapping, and we propose a new algorithm to bootstrap multiple FHEW ciphertexts, which has only a very small overhead compared to a single FHEW bootstrapping. Actually, our work is not the first one which attempts to work on the amortized cost of the FHEW bootstrapping. The previous work proposed by one of our authors, Micciancio and Sorrell, was theoretically promising, but actually their work accompanies some exponential factor as an overhead of the computational cost, and this makes it quite impractical. So on the other hand, our work has a kind of similar asymptotic amortized cost in terms of the dimension n, but we have much smaller overhead, just a linear term, contrary to the previous work. Okay, so let me start with a very brief overview on how bootstrapping works in general. The bootstrapping is defined as a homomorphic evaluation of the decryption circuit. So, for example, let's think of the very basic LWE ciphertext decryption. So it first takes the inner product of the ciphertext A, B and the secret key S, and then take some proper rounding process to remove the noise part. So the decryption is basically consists of the inner product and the rounding process. So what it means to homomorphically evaluate the decryption circuit is we first prepare the bootstrapping keys as the encryption of the secret key, which are given in public. So if you want to bootstrap the ciphertext A, B, then we compute the following things. So the first thing is we first homomorphically compute the inner product of A and S, where now S is encrypted as encryption of SI. So since these SIs are now all encrypted, the multiplication of AI and SI are actually homomorphic scalar multiplication. And also the additions are also the homomorphic additions, and the last rounding process is also a kind of homomorphic rounding operation. So assuming that we all have these tools to compute such operations homomorphically, then the result will be the encryption of the decrypted result, which is essentially the encryption of M, what we wanted. So this is the high-level overview of the how bootstrapping works and why it works. So FHEW bootstrapping is one kind of LWE bootstrapping. The distinctive point is that actually the FHEW bootstrapping performs this homomorphic decryption process in the exponent of a polynomial. So for example, when we think of a polynomial ring modulo, like very basic example like x power m minus 1, then this exponent m actually takes a role of the modulus for the exponents of all the polynomials. So this FHEW bootstrapping utilize this modulo m space of the polynomials exponents. So they prepare the bootstrapping keys as the encryption of x power si for each component si of the secret key s. And here, how we encrypt is we encrypt this polynomial, this monomial, by the ring LWE based encryption scheme called ring GSW. So the bootstrapping key is ring GSW encryption of x power si, and this is also called ring GSW register in FHEW context. So, and then the rest process is just done following the previous definition of the bootstrapping. First, we compute the homomorphic inner product process. So after the, if we assume that we have proper scalar multiplication and addition algorithms for ring GSW register, then what we can obtain is ring GSW encryption of the x power inner product result, B plus summation of AISI, right? And then the next step is to take a rounding process, and from this rounding process, we could extract the real message M from the inner product value, right? So in technical perspective, the main point is how to perform such scalar multiplication, addition, and rounding in the ring GSW register. And those are the main technical contribution of the original FHEW paper. Okay, so however, there is in fact some kind of the fundamental limitation of LWE bootstrapping, including the FHEW bootstrapping, that the computational cost is too large per each message. So for example, if you want to bootstrap multiple messages, like n messages, where the n is the dimension, then the total cost is asymptotically as large as n squared, and it is quite invisible in practical FHE parameters. So this is not about just the bootstrapping several few message or just a single message, but if we want to bootstrap like very many messages like as large as n. So from this observation, one can think of utilizing the ring LW decryption instead of LW decryption to bootstrap multiple LW ciphertext. And this is actually the basic idea of amortized bootstrapping. So the ring LW decryption looks almost same with the LW decryption, but the main difference is that now we have polynomial structure rather than a vector structure. So the inner product are actually the inner product of the polynomials. So here a times z plus b, a, z, b, all of them are polynomials. Right. So in this amortized bootstrapping, the process becomes as following. Like first, we pack multiple LW ciphertexts into a single ring LW ciphertext. And then the next step is to we homomorphically compute the ring LW decryption circuit. The first step is, as usual, we take homomorphic inner product, and then we take homomorphic rounding process. So here we need to notice that the homomorphic rounding process is essentially just repeating the existing rounding algorithm in the original few bootstrapping for each of the coefficients. So as a result, the main task we need to consider is the inner product part. The main difference with the original view is that now we need a polynomial multiplication, while the original view requires just the inner product of the vectors over some final field or the integer ring. Of course, the secret key Z is now encrypted, so it is homomorphic polynomial multiplication. To perform this polynomial multiplication as much efficient as possible, we can think of FFT, which usually gives the best performance in clear text computation. So the FFT algorithm requires addition, subtraction, and a number of scalar multiplications by the twiddle factors. So if we want to perform this homomorphic polynomial multiplication through FFT, then we need to be able to perform all the operations, addition, subtraction, scalar multiplication, all of them homomorphically. So the main advantage of FFT is, of course, the computational complexity. In clear text computation, it results in only n log n complexity, while a naive multiplication of polynomials requires n square complexity. So this figure describes the flow of the homomorphic polynomial multiplication using the naive method versus FFT method. So the naive method just the naive method means we just multiply two polynomials by regarding this multiplication as a matrix vector multiplication by expressing its polynomial with its coefficient vector and a proper corresponding matrix. And then once we interpret it as a matrix and vector multiplication, then we can actually use the homomorphic inner product algorithm in original view, the inner product between two vectors, right? So we can apply this inner product algorithm for each row of the matrix. So as you can see in this figure, you can see that each row are connected, right? So this means that each row of the matrix is used for the homomorphic inner product algorithm in the original view. So it means we repeat this original algorithm for n times because we need to repeat them each of the row. Contrary to this naive method, the FFT algorithm shows such cross computation called butterfly. So if you want to do this FFT, if we want to use this FFT algorithm, then we have to somehow homomorphically compute this butterfly structure computation. Okay, so in the previous work, actually they didn't utilize such FFT structure, but really tried to enjoy the advantage of entity domain. So when we express the inner product of polynomials with entity, then it becomes as the following equation. So the original decryption equation, the inner product part, when we just forget about the rounding process right now, for now, then it is like a times z plus b. But we can also compute this polynomial multiplication in entity domain and then come back to the positional form by taking in inverse entity. So we can have this kind of identity form. So what it means that we want to exploit this entity form of the inner product. It means that instead of preparing encryption of z, we prepare the encryption of entity of z. Then what is the main advantage? The main advantage is that in the entity domain, the polynomial multiplication is transformed into the component-wise multiplication. So if we prepare the bootstrapping key as the encryption of entity of z, not encryption of z, then we only need big O n cryptographic operations, not big O n square. So this is the main advantage, but we still have some remaining work to do. So after we homomorphically compute the inner product in entity domain, then the result is not the encryption of az plus b, but it becomes the encryption of entity of az plus b. So the remaining work is to perform homomorphic inverse entity, because what we really want is encryption of az plus b after this homomorphic inner product process. So the main bottleneck in the previous work was that the ring GSW register, which we normally use in field bootstrapping, right? This ring GSW register only supports homomorphic addition, no scalar multiplication, or even subtraction. They only efficiently support homomorphically addition. So as a result, they were not able to apply the FFT optimization for this inverse entity computation because, as I mentioned in the previous slide, the FFT requires a number of scalar multiplications with twiddle factors. So instead of using FFT, they found an alternative way called a Nussbaumer transformation, which maps each of the polynomial to bivariate polynomials where each variable has smaller degree than the original polynomial. With this new technique, the previous work could bootstrap n messages with n to the 1 plus 1 over L complexity for some parameter L, which gives n power 1 over L amortized cost. Here, the amortized cost is the total latency over the number of messages. So when we only look into the n related factors, then it seems to be quite nice result compared to just repeating the original few bootstrapping for n times, because in this case, the amortized, the total cost should be n square complexity, but now it becomes n to the 1 plus 1 over L complexity. However, in practice, the hidden exponent factor, 3 power L, becomes a very high overhead, and it results in even worse performance compared to the original view. On the other hand, our key observation is we can actually efficiently perform the homomorphic scalar multiplication in ring GSW register, which was not noticed in the previous work. And hence, we can actually apply the FFT technique for homomorphic inverse entity. So as a result, our work achieves much better asymptotic complexity because we are now using FFT instead of Nussbaumer transformation. And now we don't have any exponential factor, so that we only need to consider n power L 1 plus 1 over L factor. Surprisingly, actually there was a concurrent work which was also published to ePrint in January, actually a bit earlier than ours. And this work also addressed the amortized bootstrapping of bitwise FHE schemes like FHEW and TFHE. In short, there are several technical differences as listed here, but basically this work and our work shares the same goal and almost the same methodology, enabling homomorphic FFT in a register form, with the same observation on the scalar multiplication, that we actually can efficiently compute and perform this scalar multiplication in the ring GSW register, right? This observation, they also had the same one, and therefore both result in the same asymptotic amortized complexity. So, but still there are several technical differences in detail. So we are looking for how we can integrate those techniques together, or what is the fundamental difference of them. We are trying to look at that kind of parts. Okay, so now we'll move on to the technical parts of our work, and Gabrielle will take my baton.
Okay, let me just share my screen. Okay. Okay, can you see the screen? Is that is there anyone?
Yeah, I can see.
Okay, okay, thank you. Wait, someone wrote in the chat. Yeah, okay, perfect. Thank you for confirming. Okay, so now that Duhyeong have introduced the main idea behind our work and prior work, I will move into more detailed contribution of what we actually do in our paper. So in our work, we design, as Duhyeong already said, a new amortized FHEW bootstrapping that will operate mostly on RLWE registers, whereas previous work would focus on RGSW registers. So there are the main issues that one would face when using FFT types algorithms was the possibility to do scalar multiplications, for which we will use automorphisms, and the fact that this automorphisms can only be applied to some register, not all. And in order to remedy this, we also introduce a scheme switching technique, which allows to switch our encryption schemes from RLWE, gadget RLWE to be precise, to RGSW. And one other difference, which I will mention here, but I will not go into many details, is the fact that we will use prime cyclotomic rings instead of what is commonly used, power of 2 cyclotomics, for optimization reasons. And there's so many variants of FFT, so that's part of the choices that we make. And one of the main difficulty with using prime cyclotomic rings was the fact that we had to do a new error analysis, because most error analysis were done for power of 2, And in the case of prime cyclotomics, it is a little different. But in order to keep this talk pretty in a short amount of time, then I will not cover the error analysis for prime cyclotomics. So let me start by giving a very brief description of the FFT algorithm. So I will assume that most people here in the audience are pretty familiar with FFT, so I will not go into any details. I think one thing that one should keep in mind is that there are many variants of FFT, and there's a lot of room for improvement, optimizations at various steps of the algorithm. But here, the main idea of this more technical part of the talk is to give an idea of how it can be performed homomorphically. So bear with me for all the technical details, and you can refer to the paper for all the legal subtleties. So the general idea of an FFT algorithm is to perform polynomial multiplication, and it can be done in two general steps. Usually we evaluate polynomials at some values, which are roots of unity. And then, as Duhyeong was saying, the nice part is that once we're in the FFT domain, we can compute pointwise multiplication. So what I'm interested here are the kind of operations that need to be performed. So evaluation in the FFT algorithm will more or less follow the structure of a remainder tree. And at each layer of the remainder tree, nodes correspond to polynomials, and children of these nodes are reductions of these polynomials modulo some other polynomials. And the nice thing here about these reductions is that we will be able to have a nice form of them. And as you can see, the operations, can you see if I underline my slides? Yeah, probably, because I'm sharing my screen. The nice thing about these reductions is that the operations you can see here are additions and multiplications by these twiddle factors, so these roots of unity. As I mentioned, there's a lot of optimizations that can be done within the FFT algorithm, which I won't focus too much on. And pointwise multiplication will have similar operations, which of course we will have to perform homomorphically. So now what operations are needed homomorphically? So for the remaining of the talk, I will use a little square to denote the encrypted data. So obviously, as you probably have understood at this point, the main difficulty of FFT in our context is the fact that some of the data is encrypted. Not all of it, we have some information in the clear, but some of the information is also encrypted. And so this needs to be taken into account. And the two main operations that we will need is scalar multiplication. So some scalar A, so a ring element, which we want to multiply an encrypted data, which will give an encrypted data, and then addition of two encrypted data and addition of two ciphertexts. And now the tricky part is that the feasibility of these operations, of these homomorphic operations, will also depend on the encryption scheme that is being considered. So some of these operations won't be possible if we are using some registers. For example, as I will explain, automorphisms don't directly apply to RGSW registers, but we will be able to use them for RLWE, RLWE prime, gadget RLWE registers. So let me now describe the operation scheme, the encryption schemes that are being used. So the basis of our scheme is RLWE, so ring LWE, but there are two somehow variants of it that will be considered in our algorithm. So the first one is what we call gadget RLWE, which in our talk we will denote as RLWE prime. So the idea of gadget RLWE is to consider a gadget vector. So a gadget vector is a vector of a certain amount of coefficients. So let's say K, ring elements, and elements of RQ for the cyclotomic ring that is being considered. And gadget RLWE is going to be a vector of RLWE ciphertext where the encryption of a given message M under a certain key the encryption under RLWE prime is going to be this vector of RLWE ciphertext encrypting the message M multiplied by this all the coefficients of our gadget vector. So you can see in the formula we have RLWE of V0M, etc., RLWE of VK minus 1M. So this is how we denote a gadget RLWE, which is a vector of RLWE ciphertext. Now, similarly, we can represent an RGSW ciphertext using also RLWE type encryptions. And in particular, for RGSW, the encryption of a message M is going to be this tuple of RLWE prime ciphertext. So one is the encryption of, the second component is the encryption of M. So the RLWE prime encryption of the message M. And the first component is a secret dependent encryption where it is the encryption of Z times M. So RLWE prime of Z times M. And this is how we represent RGSW encryptions of M in our work. So these are the two encryption schemes that are going to be important in our algorithm, and they also correspond to the two registers that are going to be used. So we will mostly focus on RLWE prime registers, but for some reason that will become apparent very soon, we will also require RGSW registers. So one important operation that I just want to briefly mention here, which is useful because we will measure the efficiency of our algorithm in terms of this operation, is the O dot operation. So this is simple scalar multiplication by arbitrary ring elements, in which is going to be the building block for all the operations that we will use in our algorithm. So the O dot operation is scalar multiplication of a ring element, so an element of our ring R, and an RLWE prime ciphertext. And so it is pretty straightforward. I'm not going to read the formulas on my slide, but the idea is that you can have a ring element T and O dot, this RLWE prime encryption of M, and this operation results in an RLWE encryption of T times M. And this, I am presenting it in this slide because it will be used as I mentioned before, a building block for all the operations that we will be doing, and also because we will measure the performance of algorithms in terms of the number of these operations. So now if we go back to the homomorphic operations that are needed. So as Duhyeong mentioned in the very beginning, in a few contexts, scalar values are encoded in the exponent, meaning that if we have a value v, so a scalar v that is in ZQ, then it is mapped to the monomial x to the v. So we're considering the encryption of x to the v. So as I mentioned in our previous slide, we will be working with two types of registers, RGSW and RLWE prime, which I just introduced. And this means that for a scalar v, what we will be considered are RGSW or RLWE prime encryptions of the monomial x to the v. And now that we have the two operations that we needed in the schemes that I just introduced, we can link them together. And so in order for our algorithm to be able to run homomorphically, we will need the scalar multiplication, as I just said. So in this case, we have A times this encrypted data, which is going to be an RLWE or RLWE prime register. And to do that, we will use automorphisms on gadget RLWE, as I will present just now. And the second operation that will be needed is addition. And so in our case, addition will correspond to multiplication because we are working in the exponent. And because we don't have RLWE and RLWE prime only support multiplication by constant values, then we will use gadget RLWE times RGSW multiplication in order to perform this homomorphic addition. So I'll now introduce in more details these two operations, but again, these are the two main operations that we need to be able to perform homomorphically in order to run our FFT algorithm. So let me start with the scalar multiplication, for which we will use ring automorphisms. So I will briefly remind that an automorphism is a bijective map from a ring to itself, which for a given value t and zq star, then it sends a to the x to a to the x to the t. Now, automorphisms can be easily used for RLWE, RLWE prime registers, or ciphertext. And let me describe it with RLWE. And we got RLWE prime is a vector of RLWE ciphertext. So anything that is described for RLWE, if you want to adapt it to RLWE prime, you can just think of it as doing the same thing for every single component of the vector. So let AX and BX be an RLWE ciphertext, which is encrypted under a key SK. And let's consider an automorphism psi of t, where again, A of x is sent to A to the x of the t. Now, applying automorphisms to an RWE ciphertext is pretty straightforward. We will apply the automorphisms to all the components of the RLWE ciphertext, meaning that AXT BXT, this tuple, is going to be the RLW encryption of the message x to the t under the key SK x to the t. So here, we're all talking about polynomials. Sometimes there's the variable x that appears, sometimes it doesn't. I apologize for the lack of consistency. But the main idea here when we apply the automorphisms that it applies to all the components of RLWE. So the polynomials a and b, of course, but also the secret key sk. And now, as a result, we want the RLWE encryption of the message m to the xt. This is why we're applying the automorphisms, but we want this encryption under the key sk x, sk with a variable x, and not with a variable x to the t. And so when we apply an automorphism to the ciphertext, there's a very last step that needs to be done, which is a key switching, which is something which is pretty common, which is known for RLWE ciphertext, where we can key switch back to SKX. So here I'm not explaining the key switching process, but it is pretty straightforward. And this key switching process or function allows us to obtain an RLWE encryption of m to the xt, but under the initial secret key s to the sk to the x. Now here, it is interesting to see that automorphisms can be directly applied to RLWE and by extension also to RLWE prime, but it is complicated, or I mean, best of my knowledge, we don't know how to apply automorphisms to RGSW, because if you recall, RGSW have one of the two components, which is key dependent. So we have the encryption of a key-dependent message m times s to the k. And so the complicated part of applying automorphisms to RGSW comes from the fact that key switching becomes hard with RGSW, as we would have to key switch back also the encrypted message m times sk, because we have because the first component is key-dependent. So automorphisms in our work are applied to RLWE prime gadget RLWE registers. So this is our first of our two homomorphic operations that we will use. Now let us move to the second operation that is needed, which is addition. So addition in our case, because we're working in the exponent corresponds to a multiplication. And in our case, we will simply introduce a multiplication between an RLWE or gadget RLWE ciphertext and an RGSW ciphertext. And again, I have written down the formula for the multiplication with RLWE, but it is easily extended to gadget RLWE. And the main idea behind this multiplication is simply to use this O dot operation on the two components of the RLWE prime of the RGSW encryption registers. And so here we have a simple operation that allows to multiply two ciphertexts, which, as I just said, in the exponent will act like an addition. So let us briefly summarize what we have so far. So as Duhyeong mentioned in the introduction, we are using the notion of registers in our algorithm, as in the FHEW context, where elements of ZQ are encoded in the exponent. So every time we are thinking of the encryption of something, we're considering encryption of the monomial x to the v. So RLW prime and or RGSW encryption of x to the v. Now, there's two things we would want to do, which we are now able to do. So if we want to multiply a ciphertext by a scalar, we can use automorphisms. So again, I repeat, this is just works just for RLW prime ciphertext. And now if we have x to the a times, the ciphertext c, so x to the c times a scalar a, this corresponds to an homomorphic exponentiation as we're working the exponent. And similarly, if we want to add two ciphertexts in the exponent, then we use the RLW prime times RGS W multiplication. So at this stage, we're pretty happy. We have operations that work. The one important thing that I want to mention here for sake of completeness, but there's absolutely no details in this talk, is the error growth. So when we bootstrap, we need to keep track of the error. And one thing that is crucial when analyzing this algorithm, or just at this stage, we don't even have an algorithm yet, we just have operations. It is important to measure the error growth of these operations in order to make sure it doesn't grow too much, which we know for if we have an error at the end, which is too large, then the decryption fails. And this imposes some restrictions on some elements, for example, on the size of the secret key, the norm of the secret key. So now that we have our two operations, so what comes next? So in our algorithms, we will primarily use RLW registers. RGSW will only be needed for multiplication. And so as you can see, there's some operations that can be done with one type of register, other operations that can be done with the other one. So the natural tool that one would want at this point is some way to switch from one to the other. Because if you're on your algorithm, you have an RLWE prime register, and at some point, you need to multiply, one of the two components need to be RGSW. So ideally, you would want this tool that allows you to transform an RLWE prime register into an RGSW. So this is the next main contribution of our paper, and the next thing that I will introduce is a way to go from one encryption to another. So the input of our scheme switching is an RLWE prime ciphertext, and we want to output the RGSW encryption under the same key of the same message. So recall that the RGSW encryption of M is a tuple of two elements. We have the RLWE prime encryption of SK times M and the RLWE prime encryption of M. So the second component we directly have from the input. This RLWE prime encryption of M is exactly the input we have. So what we need, the remaining of our scheme switching technique, is to compute the first of the two components, which is the RLWE prime encryption of the key dependent message, so SK times M. So this can be done in the following way. So we will use the RLWE prime encryption of the square of SK, which we assume is given as part of the evaluation key. And then, as always for RLWE prime encryption, we can operate in parallel on each of the RLWE components. So recall that RLWE prime is this vector of RLWE components, and every time you have to deal with RLWE prime, at least in our work, you can operate on each of the components in parallel. So now assume that one of the components is this RLWE of VIM. So VI is one of the components of the gadget vector. And the idea here is to lift RLWE of VI times M to RLWE of VI times SK times M. So how will we do that? So assume we have AB, which is the RLWE ciphertext of the encryption of VI times M. The idea here is to compute A O dot RLW prime of this SK, which is provided by us from the evaluation key, and I add this B comma 0, which is a noiseless encryption of B times SK under the secret key SK. So this is not as complicated as it sounds. It is just a matter of writing things down. It is a little harder, I think, perhaps to directly understand from slides. But if you write down the various definition, it actually flows in a very simple way. So I tried to add a bit of details, but I didn't want to, overcharge the slides with too many formulas. But if we look at this computation that we're given before, so we have A O dot RLW prime of SK square, and we add this noiseless encryption, RLW encryption of B times SK. So we can write down exactly what it gives as a result. We have the encryption, the RLW encryption of A dot SK square plus B times SK. This just follows from the definition of the O dot operation and the rest. Now one can extract SK, and then we end up with the RLWE encryption of VIM plus E times SK. So this is very close to what we wanted. We wanted the RLWE encryption of VI times SK times M. The only difference is that we have an additional error term. So here we have an error E, which comes from the RLW encryption, which is multiplied by SK. And in the previous slide, I said that something that I will not mention a lot in this talk is error analysis, or how to keep track of the error. And this is an example where scheme switching introduces an additional error, which is scaled by the secret key. And this is typical example of an operation that is used a lot in our algorithm. We do a lot of scheme switchings, but we have to keep track of the fact that every time we do a scheme switching, an additional error arises scaled by SK. And so we need to choose a secret key SK with a small norm so that this multiplicative error growth remains small. So this is like little bits and pieces of error analysis, which I'm barely introducing here, but just as an example, this shows how one can happily use all the operation that one wants, but keeping track of error is also something which is very important in bootstrapping in general. So we've reached a point where now we're ready for our homomorphic FFT. I know how to scale or multiply, I know how to add stuff. And if I need to go from one scheme to another, I can use this scheme switching technique, and I can go from RLW prime, so from gadget RLWE to RGSW registers. So this is all I need for our FFT algorithm. So now if you know FFT, you can actually stop listening. I could also stop talking, but I will provide some general idea of how the algorithm goes. So going back to our fast Fourier transform. So as you probably recall from the very beginning, the second step of our amortized bootstrapping is going to be to compute this homomorphic decryption. So we want to compute AZ plus B. So in this part, I will mostly focus on the polynomial multiplication. So the plus B will arrive at the end. This is done using via fixed rotation. So we're just scaling the ciphertext by a monomial. But the core of the difficulty here is the polynomial multiplication A times Z using FFT. And the other very important thing to note here is that Z, of course, is not in plain text. We have an encryption of Z, as Duhyeong was explaining. So the FFT-based multiplication algorithm is pretty standard. This figure here is the classic FFT multiplication algorithm. The only main difference here is that I have put in boxes the values that are encrypted. So we have A in plain text, and we compute an FFT. Z, we are given an encryption of Z, but this is encrypted. The second step is in the FFT domain, where we can perform a pointwise multiplication. And then in order to go back to the encryption of A times Z, we will have to perform an inverse FFT. This is very classic. We just need to be aware of the fact that a lot of these data is encrypted. So this just summarizes what I just said. So what needs to be computed? Because the FFT is in the clear, then we can take the forward FFT as usual. The evaluation key, as I said, will contain RGSW registers of the FFT of Z. So this is something that is provided to us. And then the two homomorphic operations steps, of the algorithm that will have to be performed is pointwise multiplication and inverse FFT. And to give an idea, but at this point, you probably are well aware of the operations that are going to be performed or needed. We will have scalar multiplications in the exponent. So this particular term is the multiplication in the FFT algorithm by twiddle factors or powers of the root of unity, where the coefficients are going to be encrypted. But we will use automorphisms to do that, so we know how to do this, and then the addition of two encrypted data. And because the multiplication, so addition corresponds to multiplication in the exponent, and because one of the two encrypted data has to be RGSW and the other one gadget RLWE, then in order to add two encrypted data, we will first use a scheme switching operation in order to modify RLWE prime ciphertext register into an RGSW register, and then we will be able to perform multiplication. So this is me just repeating what I've been saying for the past slides. So I would like to show you in a bit more detail how pointwise multiplication or inverse FFT works. I'm just checking the time, but this is just to illustrate the kind of operations that we have. So let's start with homomorphic pointwise multiplication. So the goal here is to compute FFT of the product of A and Z. And at this point, we have a list of polynomials. So we have the FFT of A, which is computed in the clear, and we have the encryption of the FFT of Z. Now, as we know, pointwise multiplication, we will compute the multiplication of these A tilde I and these Z tilde I modulo some element for all the I. So if we focus on one of these multiplication and we take a very simple example, let's say we have a degree 2 polynomial here, and same for Z. If we have two polynomials A and Z taking modulo some polynomial X to the K minus zeta, and here the Z are in encrypted form, A are not. Now, the nice thing here is that the modulus has such a nice form, and we can get a very nice formula for the terms of this multiplication. This is not something that is hard to get. In particular, if we look at the inner product between A tilde and Z tilde, this corresponds to an inner product between two vectors. This is just rewriting this inner product. We have the coefficients of Z and we have the coefficients of A, which are rewritten in a different order with some of the coefficients that are multiplied by the twiddle factor. This is just a simple form corresponding to the polynomial multiplication of these two polynomials mod xk to the zeta. Now, this inner product homomorphically can be rewritten in a telescoping manner. I didn't put the formula on the slide. It is pretty long and ugly, but the core idea here will be illustrated by this figure. So I'm recalling the operations we know how to do, A times an encrypted data and the sum of two encrypted data. So how does pointwise multiplication correspond? So here we will compute one coefficient. So we're considering one product here. So recall that there's many products that has to be done. And now I'm just considering the coefficient of a single coefficient. So let's say Vj. So let's start as input to our pointwise multiplication algorithm with the RLW encryption of Z0 tilde. Now, in the telescoping formula that I have not written on this slide, the first thing that one has to do is to multiply this 0 tilde encrypted by this quantity here. So A tilde J, A tilde minus 1, J minus 1. This is in clear form. This corresponds to a scalar multiplication. And so the first operation that has to do is an automorphism. So we do this automorphism. Recall that when I say automorphism, I'm talking about an automorphisms followed by key switching. It's a little confusing because automorphisms would just be applying the automorphisms, but here recall that we have to add key switching. But this we know how to do. We're starting with an RLWE prime register, so we know how to apply automorphisms to these registers, and this corresponds to this multiplication. Now we move on in the formula that I have not written on this slide. We need to add Z tilde 1. And so here, addition in the exponent corresponds to multiplication. So Z tilde 1, recall that we have the RGSW registers of Z. So we are given of the FFTs of Z. So this is a quantity we know. And we can perform a multiplication between an RGSW register and an RLW prime register. So this multiplication is the second of the two operations we know how to do. And then the formula goes on. We multiply by A tilde G minus 1, A tilde, there's a minus 1 missing here, J minus 2. And this again is applying an automorphism to an RLW prime register. And we can move on, and at the end, we obtain the RLW prime encryption of Vj. So as you can see, homomorphic pointwise multiplication can be performed by doing a sequence of automorphisms and multiplications, which are the two operations that we know how to do. This is done for one coefficient of one multiplication, and of course the same has to be done for all the coefficients for all the multiplications. So I hope this was clear. I hope the little figure helps, but we can ask questions afterwards, of course. The next step is inverse FFT, and I'm going to go a little faster here because the idea is exactly the same. So after pointwise multiplication, we have a list of RLW encryptions of x to the Vj. So using the figure from the previous slide, we have computed the RLW encryptions of all the coefficients Vj in the exponent. So all the products, all the coefficients. But now we have this in FFT form, and we want to go back to an RLW encryption of the coefficients of AZ and not of the FFT of this. And this can be done using an homomorphic inverse FFT. Now, as I mentioned at the very beginning, I will not go into many details about FFT. I mean, actually, I won't go into any details of the FFT algorithm. But one thing to know is that the homomorphic inverse FFT can be reduced actually to a forward FFT just with an additional multiplication by the root of unity to the power -2. So at this point, what do we have? At this point of the algorithm, we have RLW registers. These are the output of the previous step of the pointwise multiplication. And the output that we want is the RLW encryption of this. And at this point here, in order to compute our homomorphic inverse FFT, we will split the registers into various groups. For each group, we will perform a standard forward FFT, and then we will multiply homomorphically each output register by a power of the root of unity. This is what I just mentioned in order to have an equivalence with inverse FFT. So step 3, we know how to do. Like, it's a multiplication, and we've settled that multiplication we can do with automorphisms. So now we can focus on step 2, but step 2 will be extremely similar to pointwise multiplication. So the idea is that, as I recalled in the very beginning, FFT will work with a remainder tree structure, and a child node will be produced if one takes the parent's node and reduce it modulo some polynomial. And the nice thing is that each reduction will result in a computation of the form, a sum of encrypted coefficients AI times powers of this twiddle factor. And again, here, you can notice that the two operations needed are multiplication by these twiddle factors and addition of encrypted data. So here I will just illustrate one layer FFT, but again, this is just to illustrate the kind of operations that are used, but at this point of the talk, I think you should be familiar with the whole process. So say, as an example, you want to compute this formula here. So we have RLW prime ciphertext, A0, A1, A2, A3, and they are multiplied by powers of zeta. So A1 times zeta, A2 times zeta squared, and A3 times zeta cubed. This can be rewritten in a different way. So this can be rewritten using this formula. It is exactly the same thing. Now, if you start on the right, the first thing we do is we start with this A3. This is an RLW prime ciphertext, and we need to multiply it by this quantity here. We apply an automorphism. Now we need to add A3 times zeta plus S2 plus A2. We need to do a multiplication. The only thing that changes from pointwise multiplication is that A2 here is an RLW prime ciphertext. So in order to perform multiplication, one of the two ciphertexts, one of the two registers, needs to be an RGSW register. And so here we perform a scheme switching. So interestingly, in our layer of FFT, we will have to do as many scheme switching as the number of coefficients -1. The first one doesn't need to be scheme switched. So we scheme switched A2. So now we have a RGSW register, and then we can perform this addition, which is our multiplication. This results in an RLW prime register, to which we need to multiply this twiddle factor. So we apply an automorphism, again, we need an addition. So we need a scheme switch A1 in order to perform the multiplication, et cetera, et cetera, et cetera. And then we move on. And this is how the evaluation for one layer of FFT for one polynomial, of course, is performed. And as you can see, the only two operations that are needed are automorphisms. The three things that are needed are automorphisms, multiplication, and scheme switching. So this pretty much finishes the description of the algorithm. So as I mentioned in the beginning here, I just described A times Z, so the whole FFT multiplication algorithm. Then we need to add B using fixed rotations. This is the main structure, the main idea of our algorithm. Now, keeping in mind that there's a fair amount of little subtleties that appear with FFT algorithms that I have not described in this presentation, but that appear in the paper. Optimizations too, and small optimizations. So now we want to analyze our algorithm. So the way we are going to analyze the performance of our algorithm is to count the number of O dot operations. So we will count the number of R O dot RWE prime operations. This is done just by analyzing every single step of our algorithm, looking at what operations are being done and how much of these operations cost in terms of O dot operation. Something that I've briefly mentioned as an example, but not talked about in detail, is the fact that we need to quantify the error growth. This is necessary for correctness. We don't want the error to become too big. In our work, we use prime cyclotomic rings, and so the error analysis slightly differs from previous work. And so at the end, when evaluating the amortized cost of our algorithm, so amortized cost meaning the cost per message, we have an asymptotic complexity of O of n to the 1 over L log n times L for some parameter L. So if we look at how this R cost compares to previous work, so if we look at FHEW and TFHE, they're sequential bootstrapping methods. So the cost is O of n, but they bootstrap only one message. Now, the previous work, this is what Duhyeong had mentioned at the very beginning, has this 3 to the L factor in front of exponential factor in front of the n to the 1 over L. So we still achieve n to the epsilon for epsilon equals 1 to the L asymptotic cost. However, the main difference is that the hidden constant is only linear in L as opposed to exponential. So we have a much smaller overhead than the previous work. The previous work being Micciancio and Sorrell from 2018. And Duhyeong also mentioned that the concurrent work published in January has also the same complexity as ours, the asymptotic complexity. So conclusion and future work. So where do we stand now? We have introduced in our paper, in our presentation, a new method to amortize FHEW bootstrapping that overcomes some of the limitations of the previous work. So we were able to fully use the FFT algorithm, and our algorithm is also much faster than the previous algorithm in terms of number of operations. Now, in order to properly evaluate the efficiency of our algorithm, ideally we would want an implementation of our algorithm, which is work in progress. The main difficulty we ran into when starting to implement or starting to think about implementing our algorithm was the fact that common libraries do not necessarily support general cyclotomics. A focus was done on power of 2 cyclotomics, which is what is commonly used in cryptography. But as the first step in potentially implementing our algorithm, we would want to first focus on better supporting what exists in common libraries for prime cyclotomics, general cyclotomics, but we mostly care about prime cyclotomics. And then what is also not written on the slide, there is still a lot of optimizations that could be done for these amortized algorithms. One restriction of FFT type algorithms is also the fact that the depth has to be a constant due to error growth. And so this factor L that you see in the asymptotic complexities is usually a constant, a very small constant. And so a better error growth analysis would also perhaps shed light on some potential improvements for these types of algorithms. And with that, I thank you for your attention. And I hope you are all here. So I cannot hear anyone.
Okay, so thank you, Duhyeong. Thank you, Gabrielle. So, other question for them?
Hello, if I can have a question, can you hear me? Yep. I would like to ask, where was the rounding step? Maybe I missed something, but Duhyeong was talking about the linear step and then the rounding step. So I was trying to follow the equation, so maybe I just missed that. Could you please tell me where it was?
No, you did not miss the rounding step. We did not present. So the rounding step is done in an extremely similar way as what was done in prior works. So in our paper and also in the presentation, we focused on the second out of the 3 steps. So we did not describe the rounding step, so you did not miss it.
Okay, thank you. Yeah, and in general, thank you for your impressive talk. Very nice. Thanks.
I may have a question. So thank you for your talk. Correct me if I'm wrong, but is the scheme switching can work with a general cyclotomic ring? Do you hear me?
So there was a bit of disconnection on the audio. So do you mean that if this scheme switching still properly work on the non-prime cyclotomic ring, right? Yeah. So of course, yeah. So our scheme switching technique does not depend on the cyclotomic ring. So it works on the general cyclotomic ring. So the main reason we used prime cyclotomic ring was to apply the FFT technique. So to apply the FFT, then we need a prime modulus, right? Then this prime, because we are doing this homomorphic operations in the exponent, the prime modulus means we need the prime degree of the cyclotomic ring. So that is the main reason we use prime cyclotomic ring, but it does not depend on the, it is independent to the our scheme switching technique.
Okay, thank you.
Can you hear me?
Yeah, I can hear you.
Oh, okay, thank you. Thank you for your presentation and genius ideas. I have another problem about the prime cyclotomic ring. I think this ring is not entity friendly. So do you take account the efficiency reduction brought by this part?
So what do you mean for the not entity friendly? So do you mean something like in case of part 2, then we can use a negacyclic entity, something like that kind of optimization?
Yeah.
Oh yeah, that's a good point. But you know, so actually we haven't taken a look into very some actual entity algorithm. What is the best one we can use for the prime cyclotomic ring? But we can also think in this perspective. So for the prime cyclotomic ring, so let's say this prime to be p, then the phi p is just p minus 1, right? So we can still use the entity for the x power p minus 1 and then reduce it to the p cyclotomic polynomial, because it just actually we have some redundant dimension 1 because there's difference between p and p minus 1, but it is not as large as the gap between, like, for example, in power of 2, if we just use a power of 2 case, if we just use x power n minus 1 polynomial, then m and the difference between m and phi m is very large, right? It is just double. So it could be a big problem, but in prime cyclotomic ring, it is just degree 1 difference. So we don't think there will be too much overhead. But I think it is still worth it that if we could find a way that if we can use p-1 dimensional entity or not.
Okay. And I still have another question that, yeah, I really think that the transformation from the gadget LWE to ring GSW is useful tools, and it have a independent interests. But do you have some efficient method to evaluate the transformation from RLWE, ring LWE to gadget ring LWE?
Yeah, it's a good question. So yeah, actually you got a good point that actually our scheme switching is from a gadget ring LWE to ring GSW, but it is not actually ring LWE to ring GSW,
Yeah.
right? So what we think is ring GSW has two components. One is the gadget, and the other one is it contains both of the encryption of message and encryption of message time secret, right? So what we have succeed in is to generate this encryption of message time secret from the encryption of message. But as you mentioned, the extension from ring LWE to gadget ring LWE, I think it is not an easy problem. So yeah, we don't know the solution for that yet.
Okay, thank you.
Yeah, thank you.
So the question, so can your work be extended to TFHE?
Oh yeah, so I mean it depends on in which perspective we say I mean there are several several differences between TFHE and FHEW, right? There have been several advanced techniques to FHE, but when we just simply think of the very basic scheme that was proposed in CGGI 2016 paper, then the main difference was like originally FHEW bootstrapping took account into the ring GSW multiplication, but in CGGI paper they introduced we can do something more efficiently by just replacing it by ring LWE times ring GSW, right? So in that perspective, I think our work is hard to be applied to the TFHE. So that is because we are using FFT technique, we need to apply this ring GSW register scalar multiplication sequentially. So sequentially means after we compute the first layer of FFT, then we need to compute second layer, and then and so on and so on. But when we want to compute, when we want to utilize the computation of ring LWE times ring GSW, then the result will be ring LWE. And then the problem is when we go to the next layer, we need somehow we need to expand this ring LWE to the ring GSW. And this is quite related to the previous question from Rita. If you want to expand ring LWE to ring GSW, then we need to know how to expand ring LWE to gadget ring LWE, but we don't know how to do this well. So yeah, so in this perspective, it is hard to apply to the TFHE external product technique.
Okay, so you need internal product, I mean, in an essential way then.
Yeah. So we need internal product, but a partial optimization is, as we introduced, we do not really need to use fully ring GSW computation, but we can utilize gadget ring LWE instead of ring GSW. So at this point, that is the maximal optimization we could achieve. And if we can find some very smart way to expand ring LW to gadget ring LW, then I think we can also expand it to the external product. It could be some independent, interesting topic.
Thank you. More questions? So if not, so I know that Jeremy has a final announcement.
Yeah, no, it's just like, no, go ahead, Mark. Sorry.
That's all I had to say.
Okay. No, me, I'm just finishing telling you guys that we are moving the monthly meetup to a weekly session to give room to more people to present. And just if anyone is interested to present, you can ping us on Discord. And that's valid for you guys, Duhyeong and Gabrielle, if you want to present further work.
Sure.
Thank you.
Thank you.
Thank you, everyone.
All right. Yeah.
Yeah.
And,
Thank you for
see
your
you
time.
next-
Thank you, everyone.
Bye-bye.
Bye.
Bye.